So start by remembering what this point was. What is the definition of that?
X in U, epsilon equals 0, and it's this n, so it's like all along the value of x minus x minus x.
That sounds right. People agree? Yeah. Nope, it started with all x of u, right? I guess it doesn't really matter what order those two go because they're universal quantifiers. And the other way of saying that is starting there, it's the definition of convergence of a sequence of numbers. How does that change to get the definition of uniform convergence?
For all x and u gets moved to somewhere around the, for all n, or n greater than n.
Yeah, somewhere in that area. Somewhere after there exists a big N. And from the lecture that happened last time, what's special about uniform convergence? I'm basically just asking what did we prove last time? I mean, there's something about continuity, right? You have a uniformly convergent sequence of functions. It used to be that in the rooms there was just like a monitor, and they would have a little sign taped down that says, please don't put the monitor on its front. And like you could just pick the monitor up and put it down sideways so that no one could see the monitor, and it said they could see the stuff behind the monitor. But then they decided that the sign doesn't work because I wouldn't obey the sign, so now they've done that. It's readable enough? Okay. Cool. So, uniform convergence is good in that if you have a sequence that converges uniformly, you automatically know the limit is continuous. In the context of, I'm going to flash forward a little bit because right now I want to be motivated by the idea of a power series. So a power series is a function like you see on page 219. Anyway, like that is just what a power series should be, right? A power series is a function what looks like that. If we're going to prove that those are continuous, well, this is a limit of a sequence of functions, isn't it? It's a limit of a sequence of, well, if you fix a single value for n, that's a polynomial. Polynomials are continuous. So power series are limits of sequences of functions. If this convergence is uniform, we get continuity of power series. So we need to show that this sequence of functions converges. So a priori, we don't even know what the limit should be. We aren't sure the limit exists. What's the strategy we have for showing that sequences of numbers have limits? If I ask, yeah.
Are you just saying like checking if the sequence is Cauchy?
Yeah. Awesome. Yeah, so to show sequences of numbers converge, we need a Cauchy criterion. To show sequences of functions converge, we need appropriate versions of the Cauchy criterion. And maybe we'll even just try to write them down straight away. No, we'll write them down as we get them. So now we'll come back to the actual pattern. So what do I want today? I want a suitable analog of the Cauchy criterion for these two contexts. So I can say a sequence of functions is pointwise convergent if and only if it's pointwise Cauchy, whatever that should mean. Uniformly convergent if and only if uniformly Cauchy. Let's try to write those down. So a sequence of functions, f sub n from u to r, is called pointwise Cauchy if, for absolutely every x in u, this sequence of numbers f sub n of x is Cauchy. Does that seem like a sensible definition to make? And that's kind of whenever a mathematician says that a sequence of functions is pointwise whatever, they just mean that for every input, that sequence is whatever. If I tell you a sequence of functions is pointwise bounded, I just mean once you fix an x and you let n vary, there's an upper bound that depends on x. That's what the word pointwise is being used to mean. So, there's a definition. A sequence is pointwise Cauchy if, for all x in u, f sub n of x is Cauchy. So just like how pointwise convergence has these two different definitions, one of which is quantified, the other one is just words, we can quantify that definition, right? If we expand the definition of Cauchy, that means that for every x in u, what's the definition of Cauchy? What should go there? Oh, maybe I'll start with this. That's definitely a thing that's in the definition of a Cauchy sequence, right?
Is it there exists a big N
Mm-hmm.
such that if little m is greater than big N and little n is greater than big N,
Yeah, I'll put that this way.
then absolute value f sub n of x minus f sub n of x is less than epsilon.
Nice. That is the definition of Cauchy just applied to this sequence. So let's put that down too. For all x in u, for all epsilon bigger than 0, there exists a choice of big N such that for all m and n bigger than big N, and let's just think about what to do intuitively. I won't worry that it's like the right thing to do yet. We'll prove it's the right thing to do. If I asked you to uniformize that definition, so big N does, doing things out of order. On what variables does this variable, if you want to prove something is pointwise Cauchy, then you would say consider any x in the domain, consider any epsilon bigger than 0, let big N be something. What things can that big N depend on? If we want to uniformize this, we want to arrange that the choice of big N doesn't depend on x anymore. So you have like the same choice of big N for all x values. How do you change the definition to do that? Well, you do something an awful lot like what we did to get the uniform convergence definition, right? You just move the for all x to after the there exists a big N. Cool. A sequence of functions is called uniformly Cauchy if exactly this definition, except the for all x is moved to somewhere after the there exists a big N. A sequence of functions is called uniformly Cauchy if for all epsilon bigger than 0, there exists a single choice of big N such that for all m and n bigger than big N, and for all x in the domain, absolute value of f sub n of x minus f sub m of x is less than epsilon. That seems sensible enough? Right, it certainly looks like a uniformized version of this definition. I should put that on the board too. As long as I'm putting everything on the board, let's put things on the board. I think this is in the opposite order from what I wrote on the page. Does it matter? No, it's all universally quantified. You can put universal quantifiers in whatever order you want, as long as you don't move a universal past an existential. Cool. So, if I have these definitions of what it means to be Cauchy, and you know what the point of Cauchy-ness is, you know what things I need to prove. I better prove these two things are equivalent, and then I better prove these two things are equivalent. Fair enough? Let's start up here, because that's going to be like super easy, because we already know the Cauchy criterion for sequences of numbers. Proposition 8.3.3, let f sub n from U to R be a sequence of functions. If f sub n is uniformly Cauchy, then f sub n is, oh no, okay. That's this. The uniform condition is stronger than the pointwise condition. If a sequence of functions f sub n is uniformly Cauchy, then it is pointwise Cauchy. Let's try to prove. So I guess start with the assumptions. Let's let f sub n be a sequence of functions, which is uniformly Cauchy. I need to show that this sucker is pointwise Cauchy. So far, so good. And we know what we need to do. And I don't know, the proof also feels obvious, right? Uniform Cauchy just means you can use the same big N for every x. Oh, so just use that big N for any particular x. Now you just have to put that into words. Consider any epsilon bigger than 0, any x in the domain U. Since f sub n is uniformly Cauchy, there is some big N, so that for all m and n, Jesus Christ. Spam. Oh, sorry, I should have my phone on mute at all times. For all m and n bigger than big N and every y in the domain, absolute f sub n of y minus f sub m of y is less than epsilon. So let me tell you why I'm using the variable y instead of the variable x. Does anyone already see the answer to that? So the variable, yeah.
Here in x is what you're trying to prove, right? It's the variable from y minus.
Yeah, and then the y is the thing that is coming from the definition of uniform Cauchy. And they have slightly different jobs, so I want to use different names for them. But I guess the point is, in the next line, I'm going to justify that I can just use the same name for both of them now. So, explain why it now follows that f sub n of x minus f sub m of x is less than epsilon as long as n and m are bigger than big N. Well, I know that this holds for absolutely every y in U. is x a particular thing in U? Oh, yeah. So since f sub n of y minus f sub m of y is less than epsilon for all y in U, and since x is in U, we can get that same conclusion. And just because, like, I feel like my presentation felt pretty flustered, let's read through this and see if it actually proves what we wanted to prove. We want to prove pointwise Cauchy. Do we start by considering any x in the domain and any epsilon bigger than 0? Cool. Do we then come up with a choice of big N? Yep, we use the choice of big N that comes from uniform Cauchy. Do we then consider any m and n bigger than that big N? Yep, I guess, like, to make it more explicit, I do that explicitly in red, in green. And then we get, yeah, there's a proof of pointwise Cauchy. Awesome. All right, so now with that out of the way, the uniform margin implies the pointwise margin. That's something that I had to prove because, like, I'm going to actually use it in a later step. Let's explore this. Let's let Fn be a sequence of functions. Then Fn is pointwise Cauchy if and only if it is pointwise convergent. So let's maybe just try to sketch out the idea of this. F sub n pointwise convergent, Fn pointwise Cauchy. So we'll try to sketch it down there, and then we'll put it into, like, formal words on the next page. What does it mean to be pointwise convergent? I mean, right, there are two choices here. I think I want to use this one this time. So for this thing to be pointwise convergent means for all x in U, f sub n of x converges. Do I know something that's equivalent to just converging? What's that? Cauchy. So this is equivalent to, for all x in U, f sub n of x is Cauchy. Oh, is that the definition of pointwise Cauchy? Oh, cool. So I guess, like, it's not written very well right now, but does that actually just look like a complete proof? And it's a proof that's, like, free of any epsilons or big N's. It just relies on the fact that we've already proven this claim, basically. So with that in mind, let's flip to the next page and actually write down that proof. So, I mean, we already know what's going to happen. It's going to be unravel the definition, say that we have the Cauchy criterion for sequences of numbers, and then put that in terms of sequences of functions. Let's let Fn be a sequence of functions. Suppose Fn is pointwise Cauchy. That means that for all x in U, Fn of x is Cauchy. According to the Cauchy criterion for sequences of numbers, that means that Fn of x is convergent. Cauchy sequences of numbers converge. Thus, this sequence of numbers converges. Let's let f of x be the limit of f sub n of x. We feel pretty good so far? All right. So this is now a function. Right, for any x in U, I have a definition for what it should mean. Does f sub n of x now converge to f of x? Yeah, like by definition. Oh, but that's exactly what it means for f sub n to converge pointwise to f on u. All right. That feel pretty good? So there's the proof that pointwise Cauchy implies pointwise convergence. Is the other direction going to be like the exact same thing again? Yeah, so I think I'm not even going to bother filling in those spaces. Any questions or complaints or concerns about this? Cool. Then let's get to the thing that's actually the meat of today, the uniform Cauchy convergence criterion. Uniform Cauchy if and only if uniform convergent. And I think I want to sketch out the logic of it first. So I guess, well, we'll start with the easy direction. The easy direction is always convergence implies Cauchy. Right, like if you look back to the proof of the Cauchy criterion for sequences of numbers, convergence implies Cauchy was the easy direction. So let's suppose that f sub n is uniformly convergent. Let's let f be the uniform limit. There's the thing I need to prove. So to prove this, what do I need to do? I need to consider any epsilon. Now I need to come up with a choice of big N. The only assumption that I have right now that might come up with a choice of big N is the fact that I know that this thing is uniformly convergent. So let's just try that choice of big N. Since f is the uniform limit, there exists some big N such that, what can I conclude? That, right? For all n bigger than big N, for all x in U, and I don't know, like there's a pattern emerging in the way that I do some of these arguments. I put that epsilon in purple because I probably don't actually want it to be epsilon by the end of the proof. I want it to be like something else, maybe epsilon over 5 or something. So let's, I don't know, any guess for, does anyone already have some intuition about what I might want to replace that epsilon by?
Maybe 2.
Let's try it. Do you have a reason for the intuition, or just like we've done usually divided by 2? All right, let's divide it by 2 and see if it works. So let's think about what we have right now. Our eventual goal, so now we can let m and n be bigger than big N, consider any x in U. My goal is if there's f sub n of x, and there's f sub m of x, I want this length to be less than epsilon. Do I know something that's already close to f sub n of x, though? Yeah, the limit. How small do I have the distance from f sub n of x to f of x right now? Do I have the same thing for f sub m of x? Yeah, m is also bigger than big N. Oh, neat. Does it look like dividing by 2 is the right thing to do? Groovy. So let's just put that in now. So now we let m and n be bigger than big N. We consider any x in U. Well, we'll add and subtract f of x and do a triangle inequality stuff. I don't know, like, do I actually need to fill in those details at this point? Cool. In fact, how many people just have done already? Yeah, add and subtract, use the triangle inequality, you'll get that. So the sequence of functions f sub n is uniformly Cauchy. That's the easy direction. Let's figure out how to do the harder direction. So let's maybe sketch it out. So we get to assume f sub n is uniformly Cauchy. We want to show f sub n is uniformly convergent. So that means I need to come up with a candidate to be the limit. And so let's start with that. Let's try to come up with a candidate first. Then we'll try to show that that candidate to be the limit is the limit. So, well, if I could find a pointwise limit for this sequence of functions, that would have to be the candidate. The uniform limit, if the uniform limit exists, it has to be the same as the pointwise limit. So, how could I get this sequence f sub n to be pointwise convergent?
We use the proposition that we proved earlier with the fact that if as uniformly Cauchy, then we know it's also pointwise Cauchy.
Nice. Since it's uniformly Cauchy, I also have that it's pointwise Cauchy. 8.3.2. All right. So I know that the sequence of functions is pointwise Cauchy. Why is that valuable? Because then it's pointwise convergent by 8.3.4. Oh, nice. So that means we can come up with a candidate to be the limit. And I know it was a million years ago that we proved that Cauchy condition is equivalent to convergence. But the hardest step in that proof is coming up with the candidate to be the limit. Once you come up with the candidate, it's not so hard to show convergence happens. And that's exactly what we'll do here. So let's put that down first, and then we'll be most of the way done. So let's suppose Fn is uniformly Cauchy. Then by 8.3.3, f sub n is pointwise Cauchy. By theorem 8.3.4, it is then pointwise convergent. Let's let f be its pointwise limit. If the uniform limit exists, it has to be the pointwise limit. So what do I need to show now? I need to show that this uniformly Cauchy sequence of functions converges uniformly to this function f, which right now I only know as its pointwise limit. That seemed like a sensible enough goal? Yeah, let's try to do it. So I want to show, let's maybe even put this in. So where are we right now? We want to show f sub n converges to f uniformly. And that's already said in this sentence, but good to say things twice. So we want to show uniform convergence. So there's what we need to show. So we need to consider any epsilon bigger than 0. Then we need to come up with a choice of big N that doesn't depend on what value of x we pick. We then consider any little n bigger than big N, any x in the domain, and get that conclusion. That's what we need to do. So, right now we have the sequence of functions is uniformly Cauchy and pointwise convergent. Let's see what we can do with that. We can't appeal to pointwise convergence yet because pointwise convergence requires us to pick an x. But we can use uniformly cosinus to get a choice of big N. Oh, nope. Uniform cosinus to get a choice of big N. Let's do that. Consider any epsilon bigger than 0. Since f sub n is uniformly Cauchy, there exists some big N, so that for all little m and little n bigger than big N and all x in U, well, like, you know what inequality I'm about to write, right? And I'm going to put the whole thing here because I think I want all of this. There exists some big N such that for all m and n bigger than big N, for all x in U, and same game, I'll put an epsilon there. We'll decide if I need to divide that epsilon by something. All right. And let's think about what my goal is. That goal would make me happy. That would get me uniform convergence. So let's try to get that. And I think here's the strategy that I'll try to play with. I have pointwise convergence, right? So that means I should be able to get like one of these two things to be close to its pointwise limit. So let's try to mess around with that. So I think here's the starting point. Does that look like an inequality I could solve for f sub m of x? In fact, it's one that I think we've done enough times already that like you can do it without writing anything. What's the upper bound you get if you solve this for f sub m of x? There's the upper bound. That's the biggest it could be. There's the littlest it could be. So far, that feel okay? All right. And I know that that's true for all m and n bigger than big N. Well, let's just remember that. There's a sequence of numbers, f sub m of x parameterized by a number little m. Do I know what the limit of that is? What is the limit of that? F of x. So that must mean, well, can I take the limit of an inequality? And I get another inequality? Except I guess strict inequalities can accidentally become loose inequalities. So they'll become less than or equal to when I take the limit as m goes to infinity, and only m. That seems sensible right now. Ooh, if we go and like muck around with that, can we put that back into something with absolute value bars in it? What do we get?
F of x minus f of x, or it's the other way.
Yeah, but who cares? Is less than or equal to. And I would like this to be less than epsilon. Is epsilon less than epsilon? Yeah, but it almost is. How should I fix the proof? Divide by 13. So let's see where we need to do that. So I guess this is where the big N comes from. So I can replace this with any positive number. Is epsilon over 13 positive? Yeah, so I can still get that. I'll get a different choice of big N, but that's fine. That will result in these two things being divided by 13. So far, so good. That'll result in these two epsilons being divided by 13. Is that now less than epsilon? How many people in their actual notes went with 13 instead of the more obvious choice of 2? I mean, it's too late for me. I'm not going to change mine. If you did that in like an actual research paper, like the referee would reply saying, "Why on earth did you divide by 13?" All right, so let's now make some observations. So the big N we found had better be independent of the choice of X. The big N came from this line, which came from uniform Cauchy. Did that big N depend on X? Good. That means we're safe so far. After we declared that big N, did we do something that involved considering absolutely any X and any M and N bigger than big N? Cool. And did we eventually get the inequality we needed? Awesome. So there's the proof that uniform Cauchy if and only if uniformly convergent. And notice, like, once we had, like, there was this idea of, like, taking advantage of the pointwise limit in some step. And that was, like, kind of a sneaky step, but not a hard step, I don't think. If you have an M and N, you want them both to go to infinity. But just let one of them go to infinity. Since you have a pointwise limit, just do it. Cool. So, there's still, like, 13 minutes left of the time slot. I've done the things that I wanted to do with today's lecture. Maybe I'll give you the following to think about. So we're coming close enough to like the end that I want you to be able to spend time focusing on this like final exam sample that I am about to give you right now. And also this midterm exam take-home version 2. And I think some of you still have to finish like midterm 1 mastery. It's like there's enough to do that I don't want to assign any more assigned homework. But here are some things to think about. We have a definition of uniform Cauchy. Do you think you could check that like some sums are uniformly Cauchy? Hope so. We're going to do power series next time, so we better be able to. So there's a sequence of functions where it's uniformly Cauchy. So does that mean that the limit of the sequence of functions should be continuous? Yeah, why?
Because we have that if the limit is you've got a uniform limit, then it's continuous, and we just showed that if you have the uniform limit, it's also uniformly Cauchy.
Nice. Yeah. I guess you have to know that each of the functions is also continuous. But if you stop that sum at some finite n, is it continuous? Yeah. Could you say some similar ones here? Okay. Did I accidentally give? No, that was not extra. One of them was for you.
Okay, I just didn't pass that.
I didn't accidentally give anyone a sample for my pre-calc exam, did I? Do I look like analysis questions?
I'd rather take the pre-calc one.
I mean, I don't know about that. Like 25 multiple choice questions, it's easy to get tired on. Like, I mean, I couldn't get 25 pre-calc questions right in a row, and I'm teaching the class. Anyway, so here are the things. Well, you know what, I think that let's just maybe do something very relaxed. So think about that next proposition, 8.3.7. Could you like do something similar to get that to be uniformly Cauchy? Yeah, and I think like you could do some stuff that's super explicit. Here's why that's weird. This function, whatever it is continuous. And like, based on your intuition that maybe you remember from like Calc 1, if a function's continuous, then it's probably like differentiable, except maybe it has some like corner points, like absolute value. Let's see that function. And like the idea is that like you can pull that up on Desmos, and that link will even go to it. Let's compute the sum from n equals, well, k equals. How far would you like to take this sum?
6,000.
I'm going to stop at 600. Desmos isn't that powerful. It might be okay with 6,000. 1 over 2 to the k times cosine of 3 raised to the k. Spelling is hard. Times x. Let's cut that off just a little bit sooner. Oh, Jesus Christ. Does that look very smooth? Looks like it's got lots of little jaggies. Oh, good. Now the parameter is now actually growing. In fact, does that look like it's got any tangent lines? There's an example of a function that is everywhere continuous, but it's all corners. There are no points where you can take a derivative of this function. And this is important in the history of analysis, that this is like one of the first examples that people saw where like you can't find a tangent line anywhere. So this got called the Weierstrass monster function. I think now it's just called the M function. And I guess we can't prove that it's not differentiable in this class because I haven't defined what the derivative is. But this idea of uniform Cauchy implies uniformly convergent, implies the limit is continuous, is a good way to come up with really badly behaved continuous functions. And it's kind of the only way. Because if you just write something down, your mind is going to think too smoothly. All right. So I don't think I want to start in on power series right now. I think I'm going to stop. I guess I'll stay here if people want to ask me any questions right now, though.
Did we get a note card on the file?
Yeah, let's say yes.
What's the parameters of
Lower, or like a paper.
Oh, yeah, we haven't done any in-class exams. I like to allow just a sheet of paper on both sides. You won't get to take it home with you, so if you want to like keep it, then make a copy of it before you come to the final.
Nothing that's off limits to write on it? Like we could
You can put definitions if you want.
draw it or something?
Yeah, sure. As a consequence, that means that like I'll make sure that all of the questions I ask on the actual exam are different enough from the things on the sample. So I'll allow the note card, but as a consequence, that means that, like I say, like I can't really give points for knowing definitions. You should just have those written down anyway. And I'll tweak any of the propositions and proofs that I'm going to ask you, so they're not so superimposed to what's on the sample. The sample is also longer than I would expect the final to be. Yeah.
Okay, so for the final, any like the valid material is the stuff like that wasn't valid starting at the end of the second midterm through the end of the semester. Is that?
Yeah. And mostly it's going to be starting with sequences of functions. Like, I mean, you'll still need to know what like the Cauchy criterion says.
Right.
And like maybe you'll come up with a sequence that turns out to be monotone. You should know that monotone sequences converge.
Okay.
Sorry, you said starting about with the sequence of functions.
Yeah. It's like basically the stuff right close to the end of the semester.
And then you said about the same length as this too?
No. That's like super long.
Okay.
If it's on one page, but yeah. The final exam is not intended to be a time crunch event. It's in the course of an hour and 50 minutes. It'll be significantly less than that's like 8 problems long or something. 7 of which are proofs, some of which are kind of hard to do. How long is it? Oh, fall from Sunday? No, I thought it was longer than that. Okay. Yeah. That is more than that. Is there a second page? Let me see what's on the webpage. I thought I remember doing something longer than that. Anyway, whatever that is a reasonable sample in terms of the problems. I guess 4 is a number of questions I would be comfortable asking. Oh, I haven't added any links whatsoever. Okay. I'll give it a look. If I meant for that to be longer, then I'll let you know. Cool.
I do have a question, but I got what we talked about.
Okay. I guess if other people want to stay and eavesdrop, that's cool.
It's just, I didn't tell you. So, I tried out that but it doesn't, that's just the hard signs. So then, I wrote it as X and equal to X and so I plus a one.
Okay.
And it's true that that's still bounded, right? Yeah.
Yeah, here's the same balance for the thing.
Yeah, okay. I don't know why I thought that would be like,
Which of the like one of the sequences converges, doesn't it?
yeah, why it does. And so then that gives me the,
So line is even better than bounded. Converges.
yeah. Yeah, so, okay, cool. Then I know what I'll do.
Okay.
I just did, I was concerned because I don't know, writing something as plus a negative seems off, but
Yeah, well, you can.
yeah,
And as long as the negative sign doesn't like interact badly with things,
yeah.
which it can if you have lim suits of limits. But not if you have the honest about limit.
Right. Yeah, and then we prove something about negative thing is like negative limb soup of that thing or something like that. So,
Okay.
and then it's convergence. Yeah. Okay. Cool. I tried it the other way for so long, and it's like the negatives just don't work out here. I thought I was